Okay, in this video we're going to look at how to solve higher degree polynomial equations like these ones. Now in the previous video, in part 4, we looked at equations that can be solved directly of a degree higher than 2. So those were equations where you can either treat them as a quadratic because only even powers appear, or you can just make z the subject of the formula because z only appears once. In this case, these equations are none of those specialized forms, so we're going to have to use the rational root theorem to start breaking them down. And then once we have got to the point where we've got a quadratic factor, then of course we can use the quadratic formula. So just to remind ourselves of the rational root theorem, it says the rational roots of the polynomial of this form will be given by the ratio or the fractions of factors of a naught, which is the constant, divided by factors of an, which is the coefficient of the leading order term. So that means in a, so let's start with a, got 2z cubed plus 4z squared plus 7z plus 5 equal to 0. So the constant in this case is 5, and the factors of 5 are plus or minus 1 and plus or minus 5. The leading order coefficient is 2, and the factors of that are plus or minus 1 and plus or minus 2. So if we divide these by plus or minus 1, we get the same numbers back. Then if we divide them by 2, we're going to have plus or minus 1/2 plus or minus 5/2. So this is going to be the set of possible real rational roots of this equation here. So if we call this thing p of x, then we can now start trying them out one by one, and then if we get one which is a root, then we can reduce the equation into a quadratic and then use the quadratic formula. So if we plug in 1, it's just going to be the sum of the coefficients 2 plus 4 plus 7 plus 5. This cannot be equal to 0. And then the next one is minus 1. If we plug in minus 1, this time we're going to get minus 2 because we've got negative 1 cubed here. So, and this one is going to be negative as well. So plus 4 minus 7 plus 5. So this time this thing works out to 0. So this is telling us that z equals to negative 1 is a root. And also it tells us that z plus 1 is a factor, which we obtain by just taking the negative 1 to the same side as the z. So that means we can divide this polynomial by z plus 1, and there should be no remainder. So if we do that using synthetic division, so we have got 2, 4, 7, 5, which are the coefficients of our polynomial here. 2, 4, 7, 5. Then using synthetic division, so bring down 2 here, multiply by negative 1, multiply by negative 1. Okay, this one of course is the remainder. So what this thing is saying is that the polynomial we can write as z plus 1 into 2z squared plus 2z plus 5. Since this is equal to 0, then this means either z plus 1 is 0, from which we already know z is negative 1, or the other one, 2z squared plus 2z squared plus 2z, not z squared, plus 5 equals to 0. Now this one, since it's a quadratic, of course we can now solve using the quadratic formula. So from that one, it means we've got negative 2 plus or minus the square root of 2 squared is 4, minus 4 times 2 times 5. So that's going to be 4 times 2 is 8, times 5 is 40. So this thing is going to be negative 2 plus or minus square root negative 36 all over 4. But square root negative 36, of course, we can write as square root 36 times square root negative 1. Square root negative 1 is I. So this is negative 2 plus or minus 6i all over 4. So this is minus 1 plus or minus 3i all over 2. So that means, in summary, the roots of our equation are negative 1 minus 1 plus or minus 3i all over 2. So that completes the first problem. The second problem is of degree 4. So this is possibly going to demand a bit more work from us. So minus 3z cubed plus z squared plus 4 equals to 0. Our a naught is equal to 4. Our an is equal to 1. So that means, by the rational root theorem, the possible roots, rational roots of this equation are going to look like this. So it's just going to be, because this one is 1 here, it's just going to be the factors of the constant which we are going to have to try out in the equation. So if we call this p of z, then of course we start with 1. So 1 is just going to be the sum of the coefficients plus 4. This one is not equal to 0. So 1 minus 3, 1, 4. Then if we try negative 1, then the powers of z, to odd numbers, will change. So it's just this one. So this time we're going to have 1 plus 3 plus 1 plus 4. This is still definitely not equal to 0. Then we go on to 2. When we plug in 2, so now we're going to have 2 to the power 4 minus 3 times 2 cubed plus 2 squared plus 4. 2 to the power 4 is 16. This one is going to be 8 times 3, which is 24. This is 4 and this is 4. Now you're going to notice here that negative 1 is only this one, 24. Then the positive one, 16 plus 4 is 20 plus 4 is 24. So this is working out to 0. So it's telling us that z equals to 2 is a root. And so z minus 2 is going to be a factor. So that means we can divide the polynomial by z minus 2, and then we're going to end up with a reduced polynomial of degree 3. So if we do that using synthetic division, so we've got 1 minus 3, 1, 0, 4. The 0 here is because this polynomial does not have a term of degree 1 here, so we put a placeholder. So that's that 0 there. So we bring down 1, we multiply by 2, we add, we multiply by 2, we add, we multiply by 2, we add, we multiply by 2. So this is telling us that our polynomial is going to be z minus 2 into z cubed minus z squared minus z minus 2. So if we call this one PR, our reduced polynomial, we now have got to try the roots for the roots of PR. Since plus and minus 1 were not roots of P, they cannot be roots of PR as well. But 2 could be a root, so we have got to start with 2. So if we plug in 2 here, this is going to be 8. That is going to be 4 minus 2 minus 2. And as luck would have it, this is actually 0. So that means z equals to 2 is a root, and z minus 2 is a factor of this reduced polynomial now. So we're going to have to divide this by z minus 2 using synthetic division. So 1 minus 1 minus 1 minus 2. So we bring down 1, we multiply by 2, we add, we multiply by 2, we add, we multiply by 2. So what's happening now is, so P of z is z minus 2 times z minus 2, then times z squared plus z plus 1. So if we set this equal to 0, then either this is equal to 0, from which we already know z equals to 2, or this quadratic is equal to 0. And this one we're going to solve using the quadratic formula. Minus b plus or minus 1 minus 4. 1 minus 4 is negative 3, so minus 1 plus or minus negative 3. So since that is a negative, it means it's going to be a multiple of I. So it's going to be I root 3. So that means the roots, in summary, are going to be 2. 2 is going to be a double root because it occurs twice. And then we're going to have these two complex conjugate roots, minus 1 plus or minus I root 3 all over 2. All right. So that is how we get to solve higher order equations involving complex roots using the rational root theorem. So the main thing here is that some of the roots must be real for this approach to work. None of the roots are real, then this approach is not going to work. In the next video, actually, we're going to do some examples where none of the roots are real, and so we're going to explain how those ones are correct. Okay, so at this point, we're going to give you the opportunity to have a go at the last two. Just pause the video, work through them, and then when you continue the video, you can compare with our solutions. All right, we're now going to scroll down to our solutions for C and D. We would like to thank you for visiting our channel and watching this video. We hope that the material is useful to you. Please do, of course, subscribe to the channel. And if you have got any questions, would be happy to hear them in the comment section. Please do like the video and share accordingly. All right. So in C, by the rational root theorem, since the coefficient, the leading order term is 1, then the possible rational roots are just factors of 4. Trying them out here, we find that 2 is a root, and so z minus 2 is a factor. So if we divide using synthetic division here, we find that the other factor is z squared minus 2z plus 2. And equating these to 0 and solving using the quadratic formula, we find that the two roots associated with that factor are 1 plus or minus I. For D, these are the possible roots. Then just trying 1, we find that that is 0. So a good practice is always just to check the coefficients of the polynomial before you try anything else. Here you see that 1 plus 1 plus 2 is 4, plus 4 is 8, and then minus 8 is 0. So straight away that tells you that 1 is going to be a root there. Then if we divide, we find that this is our reduced polynomial. Well, if we try the same thing, we're not going to be so lucky this time. 1 plus 2 is 3 plus 4 is 7 plus 8. So these ones, 1 is not going to work out. We tried out anyway for the full record, and then -1 also doesn't work. 2 also doesn't work, but -2 does work. And then using that we divide, and then now we're going to find a quadratic. It's going to be z squared plus 4. Z squared plus 4, if you solve that one, you get plus or minus 2i. These are the other two that we already found earlier. All right, thank you very much.